is the striking portion. Slight convexity is given to it to avoid digging off the edge into the job. Peen or pane. The peen is the other end of the head. It is used for shaping and forming work like riveting, peening and bending. The peen is of different shapes like the ball peen, cross peen, straight peen. The face and the peen are hardened. A ball peen hammer is used for punching, chiseling, peening, removing bends, and for straightening of sheets. Cheek. The cheek is the middle portion of the hammer head. The weight of the hammer is stamped here. This portion of the hammer head is left soft. Eye hole. An eye hole is meant for fixing the handle. It is shaped to fit the handle rigidly. The wedges fix the handle in the eye hole. The ball peen hammers are used for general work in a workshop. Clearance groove of specified form and dimensions created by removing material at an inner corner of a rotationally symmetric workpiece, and which is necessary for subsequent machining and assembly with mating parts. Types of relief grooves are as follows. Relief groove types E, F, and G are all used for different types of workpieces. Type E is used for pieces with no increased demands on the plane surface but with cylindrical surfaces which may need further processing. Type F is used for pieces with right angle surfaces which may require further machining. While type G is used for pieces which require a small transition of the right angle surfaces with less load. Now let us see job sequence for cutting square slot in workpiece. Check the given raw material for its size. Rough and finish file on surfaces flat and square to overall size of 70 by 70 by 11 millimeters. Maintaining the accuracy of plus or minus 0.04 millimeters. Mark off sizes in part 1 as per job drawing and punch witness marks. Hold part 1 in drilling machine table and drill chain drill holes to remove excess metal as shown. Periphery of the drill should not touch the witness marks. Cut and remove the chain drilled hatched part using web chisel and ball peen hammer. File the chipped portion to size and shape using safe edge file of different grades, maintaining the accuracy of plus or minus 0.04 millimeters, and check the size with vernier caliper. Cut relief grooves using hacksaw at 4 inside corners as shown. Job sequence for square insert to be fitted inside this square slot. File to size 30 by 30 by 11 millimeters, maintaining the accuracy of plus or minus 0.04 millimeters. Check the flatness and squareness with tri-square. Check the size with vernier caliper. Match Part 2 into Part 1 as shown. Finish filing in Part 1 and 2 with flat smooth file and deburr in all the surfaces and corners of the job. Apply a little oil and preserve it for evaluation.
In this video, we have learned how to mark a square slot on the workpiece using dot punch and to chain drill the marked slot without touching the periphery of the witness marks. Use of tools like chisel and hammer to remove excess material from the chain drilled slot. Maintaining the fit accuracy between the square slot and insert and create a seamless mating of the two parts. Thank you for watching. Hello everyone, welcome to this video of
Make sliding T-fit.
To create a sliding T-fit, the faces of the two mating parts must have accurate geometric tolerance to achieve interchangeability. When one component assembles properly and satisfies the functionality aspect of the assembly with any mating component, both chosen at random, then it is known as interchangeability. In this video, we will understand the limits, fits, and geometric tolerances that are required to make an interchangeable sliding T-fit.
When components are mass-produced, unless they are interchangeable, the purpose of mass production is not fulfilled. By interchangeability, we mean that identical components manufactured by different personnel under different environments can be assembled and replaced without any further rectification during the assembly stage without affecting the functioning of the component when assembled. Necessity of the limit system. If components are to be interchangeable, they need to be manufactured to the same size, which is not possible when they are mass-produced. Hence, it becomes necessary to permit the operator to deviate by a small margin from the exact size which he is not able to maintain for all the components. At the same time, the deviated size should not affect the quality of the assembly. This sort of dimensioning is known as limit dimensioning. A system of limits is to be followed as a standard for the limit dimensioning of components. Various standard systems of limits and fits are followed by different countries based on the ISO, International Standards Organization, or International Organization for Standardization specifications. The system of limits and fits followed in our country is stipulated by the Bureau of Indian Standards (BIS). Other systems of limits and fits are International Standards Organization (ISO), British Standard System (BSS), German Standard DIN. Let us now understand the Indian Standard System of limits, fits and tolerances. Whole. In the BIS system of limits and fits, all internal features of a component, including those which are not cylindrical, are designated as whole. Shaft. In the BIS system of limits and fits, all external features of a component, including those which are not cylindrical, are designated as shaft. Size. It is a number expressed in a particular unit in the measurement of length. Basic size. It is the size based on which the dimensional deviations are given. Actual size. It is the size of the component by actual measurement after it is manufactured. It should lie between the two limits of size if the component is to be accepted. Limits of size. These are the extreme permissible sizes within which the operator is expected to make the component. Maximum limit of size. It is the greater of the two limits of size. Minimum limit of size. It is the smaller of the two limits of size. Deviation. It is the algebraic difference between a size to its corresponding basic size. It may be positive, negative, or zero. Upper deviation. It is the algebraic difference between the maximum limit of size and its corresponding basic size. Lower deviation. It is the algebraic difference between the minimum limit of size and its corresponding basic size. Actual deviation. It is the algebraic difference between the actual size and its corresponding basic size. Tolerance. It is the difference between the maximum limit of size and the minimum limit of size. It is always positive and is expressed only as a number without a sign. Zero line. In graphical representation of the above terms, the zero line represents the basic size. This line is also called as the line of zero deviation. Fundamental deviation. There are 25 fundamental deviations in the BIS system represented by letter symbols, capital letters for holes and small letters for shafts. That is, for holes, capital A, B, C, D up to Z excluding I, L, O, Q and W. In addition to the above, 4 sets of letters JS, ZA, ZB and ZC are included. For fine mechanisms, CD, EF and FG are added. For shafts, the same 25 letter symbols but in small letters are used. The position of tolerance zone with respect to the zero line is shown. Fundamental tolerance. This is also called as grade of tolerance. In the Indian standard system, there are 18 grades of tolerances represented by number symbols, both for hole and shaft, denoted as ITO1, ITO, IT1 to IT16. A high number gives a large tolerance zone. Fit. It is the relationship that exists between two mating parts, a hole and a shaft, with respect to their dimensional differences before assembly. There are 3 types of fits: clearance fit, interference fit, transition fit. Job sequence for making sliding T-fit. Check the raw metal size using steel rule. File and finish to overall size of 62 by 60 by 14 mm, maintaining parallelism and perpendicularity, and to the accuracy of plus or minus 0.04 mm. Check the size with vernier caliper. Apply marking media. Mark as per drawing and punch witness marks as shown. Hacksaw and remove the hatched portion of excess metal in one side of the job. File the cut portion to size and shape, maintaining flatness and squareness to the accuracy of plus or minus 0.04 mm. Similarly, cut and remove the excess metal in other side. File and check the size with vernier caliper. Checking the raw metal size using steel rule. File and finish to the size of 62 by 60 by 14 mm, maintaining parallelism and perpendicularity to the accuracy of plus or minus 0.04 mm. Apply marking media. Mark and punch the dimension. Hacksaw, chip and remove the hatched portion of excess metal as shown. File to size and shape, maintaining flatness and squareness. Match part 1 and 2 and slide it. Finish file part 1 and 2 and deburr all the surfaces and corners of the job. Apply a little oil and preserve it for evaluation.
In this video, we have learned how to create sliding T-fit with an accuracy of plus or minus 0.04 millimeters. Thank you for watching. Hello everyone, welcome to this video of
File fit combined open angular and sliding sides.
In the previous video, we understood the procedure to make a sliding T-fit with interchangeability. We also learned about the limits, fit and tolerances. In this video, we will learn about angular measurement, geometric tolerances on shape or form, orientation and position used to file and fit combined open angular and sliding slides.
Angular measurement of angles of an object is usually expressed in degrees, minutes and seconds. 1 degree is divided into 60 minutes and 1 minute is into 60 seconds. The tool used to measure angles accurately with precision is the vernier bevel protractor. The vernier bevel protractor is a precision instrument meant for measuring angles to an accuracy of 5 minutes. The following are the parts of a vernier bevel protractor. Stock. This is one of the contacting surfaces during the measurement of an angle. Dial. The dial is an integrated part of the stock. It is circular in shape and the edge is graduated in degrees. Blade. This is the other surface of the instrument that contacts the work during measurement. It is fixed to the dial with the help of the clamping lever. Locking screws. 2 knurled locking screws are provided. One to lock the dial to the disc and the other to lock the blade to the dial. The vernier bevel protractor is used to measure acute angles less than 90 degrees and obtuse angles more than 90 degrees. The tolerance on size is also called as dimensional tolerance. But these tolerances may not be sufficient to manufacture the desired fit perfectly. So, we require additional tolerances called geometrical tolerances as shown in the example. These are of following 3 types. Tolerances on shape or form, tolerances on orientation, tolerances on position. The geometrical tolerances is represented in terms of symbol, tolerance value and reference datum. Let us see tolerances on shape or form with the following characteristics. Straightness. It is the characteristic of a line where all the elements of a line are collinear. In general, there could be 2 lines within which all the points lie on a line. Flatness. It is defined as minimum distance between 2 planes within which all the points lie on a surface. A surface where all the points lie along single plane is called as perfectly flat surface. Circularity. It is defined for a cylindrical or conical surfaces as the distance between the surface and its axis. Ideally, all points on a surface at a cross-section should be equidistant from the axis for the cross-section to be perfectly circular. The tolerance on circularity is defined by two concentric circles within which a surface can lie. The distance between the two concentric circles is called tolerance. Cylindricity. It is defined for a surface of revolution as the distance between the surface and its axis. Ideally, all points on a surface of revolution should be equidistant from the axis for the cross-section to be perfectly cylindrical. The tolerance on cylindricity is defined by two concentric cylinders within which a surface can lie. The distance between the two concentric cylinders is called tolerance. Profile of line or surface. It is defined for a line or surface of any shape as the distance between two lines or surfaces of the same shape as that of the line or surface in question, separated by a distance equal to tolerance. Tolerances on orientation. Parallelism. It is defined for a feature like surface or line with reference to another feature called reference. It defines the distance between two lines or surfaces that are parallel to each other and parallel to the datum surface and encompass the line or surface in question. Perpendicularity. It is defined for a feature like surface or line with reference to another feature called reference. It defines the distance between two lines or surfaces that are parallel to each other and perpendicular to the datum surface and encompass the line or surface in question. Angularity. It defines the distance between two lines or surfaces that are at an angle to the datum surface and encompass the line or surface in question. With respect to position, it defines the perfect exact location of a point, line or a surface in relation to the other datum. Concentricity. It defines the position of an axis in relation to the other datum axis. It defines a cylinder which coincides with the datum axis and of diameter given by the geometrical tolerance. Run out. It defines the deviation from the desired form and orientation during one full rotation of the part on the datum axis. Let us now learn the procedure to file and fit open angular and sliding sides of mating workpieces. Check the raw material for its size. File part 1 and 2 to overall size of 78 by 48 by 9 mm, maintaining parallelism and perpendicularity. Check the size with vernier caliper. Apply marking media and mark dimension lines on part 1 and 2 as per job drawing. Punch witness marks on part 1 and 2. Hacksaw and remove the excess metal in part 1. And file to size and shape, maintaining accuracy of plus or minus 0.04 mm and angle of 30 minutes. Drill diameter 3 mm relief hole in part B. Chain drill. Chip, remove the excess metal in part B. And file to the size and shape. Check the size with vernier caliper and angles with vernier bevel protractor. Finish file on part 1 and 2 and deburr in all corners. Match part 1 and 2 as shown. Apply a little oil and preserve it for evaluation.
In this video, we learned how to take angular measurements and use of vernier bevel protractor, concept of geometric dimensioning and tolerancing GD and T,
How to file fit combined open angular and sliding sides of mating workpieces.
Thank you for watching. Hello everyone.
Welcome to this module of File Internal Angles 30 Minutes Accuracy Open Angular Fit.
In this video, we will learn to read angular measurements using bevel protractor, understand parts of a vernier caliper, and to read a vernier caliper as per the required accuracy. We will also understand the procedure to file internal angles with 30-minute accuracy for angular fit.
A vernier bevel protractor is used to take angular measurements. There are 2 graduations. The main scale division, MSD. For purposes of taking angular measurements, the full circumference of the dial is graduated in degrees. The 360 degrees are equally divided and marked in 4 quadrants, from 0 degree to 90 degrees, 90 degrees to 0 degrees. Every 10th division is marked longer and numbered. Each division represents 1 degree. The graduations on the dial are known as the main scale divisions. The vernier scale division, VSD. On the disc, 23 divisions spacing of the main scale is equally divided into 12 equal parts on the vernier. Each third line is marked longer and numbered as 0, 15, 30, 45, 60. This constitutes the vernier scale. Similar graduations are marked to the left of 0 also. The least count of the vernier bevel protractor. When the 0 of the vernier scale coincides with the 0 of the main scale, the first division of the vernier scale will be very close to the second main scale division. Now, 1 MSD is equal to 1 degrees. 1 VSD is equal to 23 by 12 degrees. Hence, the least count is calculated as least count is equal to 2 MSD minus 1 VSD, which is equal to 2 degrees minus 23 by 12 degrees, which is equal to 24 minus 23 by 12 degrees, which is equal to 1 by 12 degrees since 1 degree is equal to 60 minutes, which is equal to 1 by 12 degrees into 60, which is equal to 5 minutes. Therefore, least count of vernier bevel protractor is equal to 5 minutes. For reading acute angle setup. First, read the number of whole degrees between 0 of the main scale and 0 of the vernier scale. Note the line on the vernier scale that exactly coincides with any one of the main scale divisions and determines its value in minutes. To take the vernier scale reading, multiply the coinciding divisions with the least count. Example, 10 into 5 minutes is equal to 50 minutes. Total up both the readings to get the measurements, which is equal to 41 degrees 50 minutes. If you read the main scale in an anti-clockwise direction, read the vernier scale also in an anti-clockwise direction from 0. The vernier scale reading up is taken on the left side as indicated by the arrow. The reading value is subtracted from 180 degrees to get the obtuse angle value. Reading is 22 degrees 30 minutes. To subtract reading value from 180 degrees. Measurement is equal to 180 degrees minus 22 degrees 30 minutes, since 1 degree is equal to 60 minutes, which is equal to 179 degrees 60 minutes minus 22 degrees 30 minutes, which is equal to 157 degrees 30 minutes. Care and maintenance of vernier bevel protractor. Clean the vernier bevel protractor before use. Loosen the locking screw of dial to move the blade according to the angle measurement. While taking a measurement, apply light pressure on vernier bevel protractor. Heavy pressure will force the two scales out of parallel and show the false reading. After using vernier bevel protractor, wipe it clean and apply a thin coating of oil and keep it in safe place. Now let us see the different parts of a vernier caliper. Fixed jaws 1 and 2. Fixed jaws are part of the beam scale. One jaw is used for taking external measurements and the other for taking internal measurements. Movable jaws 3 and 4. Movable jaws are part of the vernier slide. One jaw is used for external measurements and the other for internal measurements. Vernier slide 5. A vernier slide moves over the beam and can be set in any position by means of a spring-loaded thumb lever. Beam 6. The vernier slide and the depth bar attached to it slide over the beam. The graduations on the beam are called the main scale divisions. Depth bar 7. The depth bar is attached to the vernier slide and is used for measurement of depth. Thumb lever 8. The thumb lever is spring-loaded, which helps to set the vernier slide in any position on the beam scale. Vernier scale 9. The vernier scale is the graduation marked on the vernier slide. The divisions of this scale are called vernier divisions. Main scale. The main scale graduations or divisions are marked on the beam. Determining the least count of vernier caliper. 49 main scale divisions are equal to 50 vernier scale divisions. Therefore, 1 VSD is equal to 49 upon 50 millimeters. 1 MSD is equal to 1 millimeters. Least count is equal to 1 MSD minus 1 VSD, which is equal to 1 millimeter minus 49 by 50 millimeter, which is equal to 50 minus 49 by 50 millimeters, which is equal to 1 by 50 millimeters, which is equal to 0.02 millimeters. Therefore, least count of vernier caliper is equal to 0.02 millimeters. 1 inch of the main scale is divided into 10 major divisions, and each of these is further divided into 4 equal parts. The value of each division is 1 by 10 into 1 by 4, which is equal to 1 by 40 inches, which is equal to 0.025 inches. One main scale division is divided into 25 divisions on vernier scale. Therefore, least count is equal to 1 by 40 inches divided by 25, which is equal to 1 by 40 inches into 1 by 25, which is equal to 1 by 1000 inches, which is equal to 0.001 inches. Therefore, least count of vernier caliper is equal to 0.001 inches. To file internal angles with 30-minute accuracy for angular fit. Check the raw material size. File part 1 and 2 to overall size 74 by 47 by 9 mm, maintaining flat and squareness. Apply marking media on the surface and mark dimension lines on part 1 and 2 as per job drawing. Punch witness marks on part 1 and 2. Drill diameter 3 mm relief holes in part 1 and 2. Hacksaw and remove the excess metal in part 1 and file the cut portion to size and shape. maintaining the accuracy plus or minus 0.04 millimeters and angles 30 minutes. Chain drill, chip, hacksaw, and remove the excess metal in part 2 and file to size and shape. Check the size with vernier caliper and angles with vernier bevel protractor. Match part 1 and 2. Apply a little oil and preserve it for evaluation.
In this video, we learned to measure angles accurately by understanding the graduations and least count of the vernier bevel protractor, different parts of vernier caliper and its least count to measure linear dimensions accurately, procedure of filing internal angles to a 30-minute accuracy and matching sliding paths to create an angular fit. Thank you for watching. Hello everyone. Welcome to this video of Make and Assemble Sliding Flat Plane Surfaces. In this video, we will gain an understanding of taps, reamers, and their parts. Additionally, we will learn practical skills to make and assemble sliding flat plane surfaces.
Hand taps are used for internal threading of components. They are made from high carbon steel or high-speed steel, hardened and ground. Threads are cut on the surface and are accurately finished. To form the cutting edges, the flutes are cut across the thread. For holding and turning the taps while cutting threads, the ends of the shanks are squared. The end of threaded body of the taps are chamfered, taper-led, for assisting, aligning and starting of the thread. The size of the taps, the type of the thread, and pitch are usually marked. Generally, circles are marked to indicate the types of taps. One circle, first tap or taper tap, is to start the thread. Two circles, second tap or intermediate tap. Three circles, plug tap or bottoming tap or finishing tap is used to finish the threads of a blind hole to the correct depth. These taps are identical in all features except in the taper lead angle. Tap wrenches are used to align and drive the hand taps correctly into the hole to be threaded. Tap wrenches are of different types. Double-ended adjustable tap wrench or bar type tap wrench. This is the most commonly used type of tap wrench. It is available in various sizes. These tap wrenches are more suitable for large diameter taps and can be used in open places where there is no obstruction to turn the tap. It is important to select the correct size of wrench. T-handle tap wrench. These are small adjustable chucks with two jaws and a handle to turn the wrench. This tap wrench is useful to work in restricted places and is turned with one hand only. This wrench is not available for holding large diameter taps. Solid type tap wrench. These wrenches are not adjustable. They can take only certain sizes of taps. This eliminates the use of a wrong length of the tap wrenches and thus prevents damage to the taps. What is a reamer? A reamer is a multi-point cutting tool used for enlarging by finishing previously drilled holes to accurate sizes. Reamers are classified as hand reamers. Reaming by using hand reamers is done manually, for which great skill is needed. Hand reamers have straight shanks with square at the end for holding with tap wrenches. Machine reamers are fitted on spindles of machine tools and rotated for reaming. They are provided with Morse taper shanks for holding on machine spindles. Parts of a hand reamer. Axis, the longitudinal center line of the reamer. Body, the portion of the reamer extending from the entering end of the reamer to the commencement of the shank. Recess, the portion of the body which is reduced in diameter below the cutting edges, pilot or guide diameters. Shank, the portion of the reamer which is held and driven. It can be parallel or taper. Circular land. The cylindrically ground surface adjacent to the cutting edge on the leading edge of the land. Bevel lead. The bevel lead cutting portion at the entering end of the reamer, cutting its way into the hole. It is not provided with a circular land. Taper lead. The tapered cutting portion at the entering end to facilitate cutting and finishing of the hole. Bevel lead angle. The angle formed by the cutting edges of the bevel lead and the reamer axis. Taper lead angle. The angle formed by the cutting edges of the taper and the reamer axis. Terms relating to cutting geometry. Flutes. The grooves in the body of the reamer to provide cutting edges, to permit the removal of chips and to allow the cutting fluid to reach the cutting edges. Heel. The edge formed by the intersection of the surface left by the provision of a secondary clearance and the flute. Cutting edge. The edge formed by the intersection of the face and the circular land or the surface left by the provision of primary clearance. Face. The portion of the flute surface adjacent to the cutting edge on which the chip impinges as it is cut from the work. Rake angles. The angles in a diametral plane formed by the face and a radial line from the cutting edge. Clearance angle. The angles formed by the primary or secondary clearances and the tangent to the periphery of the reamer at the cutting edge. Helix angle. The angle between the edge and the reamer axis. Moving on to make and assemble sliding flat plane surfaces. File job for part 1, 2, 3 and 4 to size and shape as per drawing. Apply marking media on part 2 and 3. And mark to locate the dowel pin holes, countersink screw holes as per drawing. Assemble and clamp part 1, 2, 3 and 4 together in drilling machine table with parallel clamps. Fix diameter 3.8 mm drill in drilling machine spindle. Through drill chuck and drill through hole. Fix diameter 4 mm hand reamer in tap wrench and ream the drilled hole to fix diameter 4 mm dowel pin without disturbing the assembly setting. Clean the reamed hole and insert diameter 4 mm dowel pin. Similarly, drill holes for other 3 dowel pin holes one by one and ream the drilled holes one by one and fix the dowel pins without disturbing the assembly. Fix diameter 4.2 mm drill in drilling machine spindle through drill chuck and drill holes for tap drill holes for fixing countersink screws in assembly without disturbing the setting. Separate the assembly parts 1, 2, 3 and 4 and chamfer the tapping holes both ends in part 1 using countersink tool. Hold part 1 in bench-wise. Drill free hole diameter 5.5 for countersink screw on part 2 and 3 and countersink the hole to seat countersunk head screw. Cut internal thread using M5 hand tap and tap wrench. Clean the thread without burrs. Assemble part 1, 2, 3 and 4 as per job drawing along with dowel pins and countersink screws. fit and slide part 4 in the assembly. Disassemble all the parts from assembly. Finish file on the surface of part 1, 2, 3 and 4 and remove burrs in the corners of the job. Reassemble all the parts together as per job drawing. Apply thin film of oil and preserve it for evaluation.
In this video, we learnt about taps and reamers, practical skills to make and assemble sliding, flat, plane surfaces. Thank you for watching. Hello everyone.
Welcome to this module of Check for Blue Match of Bearing Surfaces, both flat and curved surfaces by Whitworth method.
In this video, we will understand need for scraping surface, Whitworth principle and checking for blue match of bearing surfaces, both flat and curved surfaces by Whitworth method.
How does one obtain a flat surface? If three plates are compared with one another in alternate pairs, they will only mate perfectly in all positions when they are absolutely flat. File and ensure that all the three plates are finished to size and square. Stamp the plates X, Y and Z with a letter punch. Apply a very thin uniform coating of Prussian blue on the faces of plates X and Y, which are to be scrapped. Keep both the pieces together and rub the plates back and forth against each other. Observe the high spots on the plates X and Y, remove by scraping with knitted cotton cloth. Rub with an oil stone gently to remove the burrs and again clean with knitted cotton cloth. Repeat the same procedure till both the faces are mating with good bearing surfaces. Apply a very thin uniform coating or Prussian blue on the face of the plate Z, which is to be scrapped. Keep the faces of the plates X and Z together and rub the plates back and forth against each other. Observe the high spots on the plate Z and remove by scraping. Repeat the same procedure till both the faces of the plates X and Z are mating with good. Repeat the procedure till the faces of plates Y and Z are mating with good bearing surfaces. Now, one cycle of operation is completed. Plate X will mate with plates Y and Z, but Y and Z will not mate. All the three plates mate only when all the three are flat. So, repeat the cycle a number of times till interchangeable, flat, good bearing surfaces are achieved. For scraping flat surfaces, the following two scrapers are used. Flat scrapers with rectangular blades. Used for scraping large flat surfaces. The working edge is not thicker than 3 mm. Hook scrapers with rectangular blades. Used for scraping the center portion of large flat surface where it is not convenient to use flat scraper. A half-round scraper is the most suitable scraper for scraping curved surfaces. For scraping curved surfaces, the handle is held by hand in such a way as to facilitate the movement of the scraper in the required direction. Pressure is exerted with the other hand on the shank for cutting. Rough scraping will need excessive pressure with longer strokes. For fine scraping, pressure is reduced and the stroke length also becomes shorter. Cutting action takes place both on forward and return strokes. During the forward movement, one cutting edge acts and on the return stroke, the other cutting edge acts. After each pass, change the direction of cutting. This ensures a uniform surface. Use a master bar to check the correctness of the surface being scraped. Apply a thin coating of Prussian blue on the master bar to locate the high spots. For scraping on flat surface, check the raw material for its size. File metal to size 96 by 96 by 10 mm, maintaining flatness and squareness. Check the size with vernier caliper. Clean the surface plate with soft cloth. Apply Prussian blue evenly on the surface plate. Place the job on surface plate and move slightly forward and backward. Take the job from surface plate and notice the blue spotted marks on the flat surface. Hold the job in benchwise. Scrap and remove the high spots on the flat surface of the job using flat scraper. Wipe off the scraped surface with soft cloth to remove burrs. Again, place the scraped surface on Prussian blue applied surface and move forward and backward and notice the high spot marks. Repeat the scraping process until the Prussian blue spotted marks spread over the entire surface of the job. Wipe off the scraped surface with soft cloth. Apply thin coat of oil and preserve it for evaluation. Now, checking the blue match on flat surface. After scraping the flat surface, clean the surface plate with soft cloth. Apply Prussian blue evenly on the surface plate. Place the job on the surface plate. Move slightly forward and backward and notice the blue match spread over the entire flat surface. For scraping on curved surface, check the raw material for its size. File metal to size 90 by 48 by 18 mm, maintaining flatness and squareness. Check the size with vernier caliper. Apply marking media, mark and punch. Chain drill holes remove excess material. Cut and remove the hatched portion of chain drilled holes, excess metal using web chisel and ball peen hammer. File curved surface with half round file and check the curved profile with template. Hold the round test bar diameter 60 mm in bench vise along with vise clamps. Apply thin coat of Prussian blue on the one end of cylindrical surface of test bar. Place the curved surface of the job on Prussian blue applied test bar and rotate back and forth. Notice the blue spotted marks on curved surface. Hold the job in bench vise. Scrap and remove the high spots on the curved profile surface using half round scraper. Wipe off the scraped surface with soft cloth to remove burrs. Again, apply Prussian blue on the test bar and place the curved scrapped surface on test bar and rotate back and forth. Repeat the scrapping process until the Prussian blue spotted marks spread over the entire curved surface of the job. Wipe off the scraped surface with soft cloth. Apply thin coat of oil and preserve it for evaluation. to check the blue match on curved surface. After scraping the curved surface, clean the cylindrical test bar with soft cloth. Hold the test bar in bench vise along with vise clamp. Apply Prussian blue evenly on the curvature of the test bar. Place the curved surface of the job on test bar and rotate slightly on back and forth. Notice the blue match spread over the entire curved surface.
In this video, we learnt to originate flat scraped surfaces by the 3-plate method or Whitworth principle, to check for blue match of both flat and curved bearing surfaces. Thank you for watching.
Hello viewers, welcome to another